Today we're going to talk about what causes race conditions and how to fix them using a semaphore. Specifically, we'll use a mutex, which is just a semaphore with a count of 1. This is an autism-friendly coding tutorial. Calm pace, no jargon, and everything explained step by step. By the end of this video, you'll understand why race conditions happen and how controlled access fixes them. For the purpose of this tutorial, we're going to simulate a very simple scenario. We'll start with an account balance of $100. Then we'll attempt 50 withdrawals of $5 each, all happening around the same time. In a correct system, only 20 of those withdrawals will succeed, and the final balance should be 0. That expectation is important, because it gives us a clear way to tell whether the code is behaving correctly or not. In this next slide, we'll look at code that tries to do this, but does it in an unsafe way. At a glance, this code looks reasonable. We're just simulating 50 attempted withdrawals of $5 each. You might expect that after 20 withdrawals, the balance would reach 0, and once the balance reaches 0, you might expect the remaining withdrawals to fail. If that were true, the code would report exactly 20 successful withdrawals, but that's not what actually happens. As demonstrated here, the number of successful withdrawals is higher than expected, and the simulated balance doesn't reach 0. The program finishes normally. There's no error message. In the next step, we'll slow this down and talk about why this happens. The key issue here is execution order. Each withdrawal runs asynchronously, and JavaScript does not guarantee the order in which those asynchronous operations will complete. Because of this, multiple withdrawals are able to read the same balance value before any one of them finishes updating it. They each believe the money is still available, so more withdrawals succeed than should. This isn't about randomness causing a bug. The random delay just makes the timing differences easier to see. The real problem is shared state being accessed without any control over who updates it and when. That combination, unpredictable order and shared state, is what creates the race condition. So now that we understand the problem, let's talk about the kind of tool that solves it. The issue isn't that the logic is wrong. The issue is that multiple operations are allowed to touch shared state at the same time. A semaphore is a way to control that. At a high level, a semaphore is just a counter that represents permission. It says how many operations are allowed into a critical section at once. If the count is greater than 0, an operation can proceed. If the count is 0, the operation has to wait. A mutex is the simplest form of a semaphore. It's just a semaphore with a count of 1. That means only one operation can enter the critical section at a time, and that's exactly what we want when we're updating something like an account balance. In the next step, we'll look at how this is implemented in code. At the top, we define a semaphore class. It keeps track of two things: a count, which represents how many permissions are available, and a queue, which holds operations that are waiting for permission. Next is the acquire method. When an operation calls acquire, it checks whether the count is greater than 0. If it is, the count is decreased and the operation can continue immediately. If the count is 0, the operation can't proceed yet. In that case, it waits until permission becomes available. Then we have the release method. When release is called, we check whether anything is waiting. If something is waiting, the next operation is allowed to continue. If nothing is waiting, the count is increased. Finally, we have the use helper. This wraps the acquire and release logic safely. It makes sure permission is always released, even if something goes wrong. This code doesn't solve the problem by itself. It just gives us a way to control access. In the next step, we'll use this to fix the demo. Here's how we use our newly created semaphore class in our program. At the top, we create a mutex by creating a semaphore with a count of 1. That single permit means only one withdrawal is allowed to update the balance at a time. Next, we reset the simulated balance at the start of the run. Now we get to the withdrawal function. This function looks almost identical to the earlier version. The difference is that the read, check, and update of the balance all happen inside a call to mutex.use. That ensures those steps happen as one uninterrupted unit. While one withdrawal is running inside that block, all others have to wait. Finally, we start the withdrawals and report the results. The logic didn't change, the access did. In the next step, we'll look at what happens when we run this version. Here's a pre-recorded run of the updated version. We're running the same scenario as before, but now access to the shared balance is controlled. The demo reports exactly 20 successful withdrawals, and the simulated balance reaches 0. The program finishes normally. There's no error, and this time the result matches our expectations, and even if the timing changes, the outcome stays correct. Let's wrap this up with the core ideas. Execution order is not guaranteed. When multiple operations run asynchronously, the order they finish in can change. Shared state needs controlled access. If more than one operation can read and write the same value at the same time, oftentimes correctness depends on timing, and the mutex protects updates until they're complete. By allowing only one update at a time, we prevent overlapping changes and eliminate the race condition. If this kind of direct autism-friendly tutorial is helpful, subscribing is a great way to find your way back here. These videos are designed to move at a calm pace, explain things clearly, and show the full code so that you can actually follow what's happening. Thank you for watching, and let's keep learning and growing together. Oh, and one more thing. Recently, I've released the ComCoder Desk cards. They're a printable set of 25 affirmation cards designed to support focus, reduce overwhelm, and encourage self-trust during coding sessions, especially for autistic and ADHD minds. Each card offers a quiet, grounded reminder you can glance at while debugging, working through a difficult problem, or feeling stuck. If that sounds useful to you, you can find the link in the video description.